Good. Okay. Thank you, Leo. So good afternoon. My name is Rosanna Norman. I'm the communications manager for Geant. Thank you very much for joining our penultimate webinar for this year's Cybersecurity Month campaign, which focuses on social engineering with the tagline, "Your brain is the first line of defense." For those of you who are not familiar with Geant, just let me give you a little introduction. Geant is the organization that delivers a worldwide network and a portfolio of services for research and education exclusively. We operate a pan-European infrastructure, which is called the Geant network. So, and at the same time, we run a membership association for Europe's NRENs, National Research and Education Networks, and which is called the Geant Association. The CSM24, with the Cybersecurity Month 2024, we aim to encourage users to think critically and remain vigilant, enabling them to stay one step ahead of cybercriminals. Okay, along the 4 free webinars that have been taking place, this year our campaign includes a variety of other activities, a series of videos, and of course, if you're on social media, or if you can connect to our Connect website, you will be able to follow the adventures of Jake Doubt. And if you don't know who that is, I encourage you to go and check it out. So then also we've been having videos with tips and tricks from community experts, blogs, articles, and so more. But back to our webinars. So today we are very excited to have with us Dr. Luisa Verdoliva from Università Federico II di Napoli, in Naples, Italy. Luisa is a full professor and leads a multimedia forensics lab. Her scientific interests are in the field of image and video processing, with main contributions in the areas of multimedia forensics. Going back to the specifics of to the theme of the webinar today, so basically with the rapid progress of recent years, techniques that generate and manipulate multimedia content can now provide a very advanced level of realism. The boundary then between real and synthetic media has become very thin. So this talk aims to present an analysis of the methods for synthetic media verification. So at the end of the webinars, we will have time for questions. So the webinar should last around 45 minutes and 15 minutes for questions. So please feel free to use the chat for questions throughout the presentation. So all I need to do is to pass the microphone to Luisa, and the floor is all yours. Thank you.
Thank you, Rosanna. Thank you for this kind presentation, and good afternoon to everybody. I'm very happy to be here and to present this talk, which is, as Rosanna said, this is about synthetic media verification in the era of generative AI. And in particular, we will see a bit what are the most successful methods in this area, and what is actually working and what is not there yet. Okay, so I mean, I probably you have already seen these synthetic images, and in the last years there has been a very rapid evolution of synthetic content generation. In this slide, you can see some fully generated images using generative adversarial networks, and I mean, these are all synthetic, so all fully generated, and still the quality is very high. More recently, probably you have heard about diffusion models, where you can generate an image by using simple text descriptions. So you just write a sentence and you can easily generate such image. And not only fully generating an images, but you can also locally manipulate one. So here is my PhD student who actually took his photo, and he then wrote a sentence, a cat in the backpack, and in a moment actually has the manipulated image. These are also text-driven image generation, and this was generated using Adobe Firefly. Also, videos can be easily manipulated. Here, there are some examples of deepfake videos where on the top you can see the original videos, and on the bottom, what are called the in-painted videos where objects have been removed. And also here, you can notice that the quality is quite high. And probably you have already seen also these examples of Sora, and where all these videos have been fully generated using text descriptions again. So you can not only modify an image, but you can also generate a completely synthetic videos with a very high quality. And other examples are these ones. You can start from an image and you can generate a video. So you can apply audio to video generation. So here you can see an example. Or in general, I mean, you have a lot of such examples over the web. And here again, these are examples that have been downloaded from internet. And of course, some of them are just there for some, only for fun, but you can see on the left, I mean, you can use them also to spread this information. And also for AI-generated images, there are plenty of such images over the web, and some of them also went viral. And okay, so what can we do? How can we defend against fake content? Actually, my research is on developing methods that can distinguish real content from fake ones. And this is about, so multimedia forensics is actually the main research topic I work on. And what is the point is this. Actually, it's very difficult for a human to distinguish a real image from a generated one. And there are some studies on this where they show that the average accuracy is around 50% for untrained observer and 60% for trained observers with unlimited time. And this study was published in 2021, which is a few years ago, when the quality of the generated content was not as good as today. So, of course, it's really very difficult from visual inspection to distinguish a real image, video, or even an audio from generated ones. So how can we develop an automatic tool for deepfake detection? First of all, let's say that I work on passive methods, which means a method that provides a global integrity score or a localization map. So suppose that we have this image and we want to have a number, a score that tells us if the image was manipulated or not. So which is actually proportional to the probability that the image was manipulated. But we will also would like to localize the manipulation. So obtained what is called an heat map or a localization map, where we can say, okay, in the red area, the image was manipulated. And how these methods work. So most of the detection approaches look to some specific inconsistencies. And we can distinguish two different types of artifacts, what are defined high-level artifacts and what are the low-level artifacts. So the high-level artifacts are more related to illuminations, shadows, lack of symmetry, so some sort of semantic inconsistencies or physical inconsistencies, and often this type of artifacts can also be spotted by visually, and I will show to you this in a moment. And then there are these low-level artifacts, which instead are related to hidden traces inside the image. And I will talk a lot about this because this is actually the topic on which the main topic of my research. So visual artifacts. So you can, especially at the beginning when these synthetic images were these synthetic generators were developed. So let's say in around 2017, 2018, there were the first high quality generative adversarial networks. The generated images could present some color anomalies, and you can see here in the images these weird regions, or lack of symmetry. So for example, in this case, you can see different color of the eyes, or ears are not perfectly symmetric. And also here, in this image is characterized by some semantic artifact, which is not easy to be spotted. But if you if we make it zoom, we can see that there are corneal specular highlights inconsistencies between the two eyes. So this white circle is actually in a different composition compared to the other one. And there are also different type of semantic artifacts like errors related to shadow or to perspective. And this is a very recent work that was published this year and refers to the most recent generators. Of course, visually, it's not really easy to spot this, but by developing an automatic algorithm, it is possible to see that there are some inconsistencies. Now, the main and over the web, on the literature, there are really a large number of methods that are based on these high-level features. And here I show just some examples. There are a lot on deep fakes on people, like eye blinking, as I told you, symmetry of eyes or corneal specular highlights, but also heart variations and head pose inconsistencies. Now, the main problem of this type of methods is that technology is advancing very fast. So, for example, the more recent face generation methods do not present the inconsistencies I have shown to you before. So, just after 1 year, 2 years, the problems that characterize the older synthetic generators are not here anymore. And also, this is a very, very recent tool that is available online. It's called Flux. And you can see how realistic and how high is the resolution of such images. This is really impressive. Also for me, who actually work in this field since a long time. It's actually 15 years I work in the field of detecting manipulation, and also, of course, in trying to understand how all these generative methods work. So if we do not consider these high-level artifacts, let's go to these low-level artifacts. What are these hidden artifacts that are present in an image? Now, an image is captured using an acquisition system where there are, of course, hardware components, but also different processing that are carried out inside the camera, like, for example, lens distortion correction, white balancing, demosaicing. And all these operations introduce some specific correlations inside the image and a specific signature, which means that actually as soon as the image is manipulated or modified, this sort of embedded fingerprint will be also modified. And this is something that is very well known in the literature, since cameras, in each camera there is this photoresponse non-uniformity, PRNU, that originates from the imperfections in the sensor manufacturing process. And this can be modeled as a multiplicative noise. It's embedded in every picture, and it's a fingerprint for each device. So this means that we can distinguish two different devices because of this fingerprint that was originated by imperfections in the process, in the manufacturing process. And this is very powerful, of course, because what we can do is actually compute this PRNU by taking like 100, 200 real images from the device, then remove the scene content and make a sort of average of what are called the residual images. And we can, this is a quite simple procedure, I'm telling you to extract this PRNU. Now, if we have an image that is coming from the same device, and we remove the scene content, so we estimate this PRNU, what we can do is to compare the PRNU fingerprint with this correlation field, and you can see that the correlation field is green, yellow, red, but then there is an area which is blue. This blue area means that there is a lack of the fingerprint. So a lack of the fingerprint means that there is a modification of the fingerprint itself. And so the image was manipulated. So in this case, we have that the red object in the image was inserted. And this is very powerful. I mean, of course, you cannot see any type of inconsistencies visually in the image, but there are hidden traces in the image that should be properly extracted. So can we also say that an AI-generated images also present a sort of artificial fingerprint? At the end, I mean, while a real image is taken from a camera, and of course, which is a real camera, an artificial fingerprint, an artificial image is in any case generated. So for example, this image is generated using a convolutional neural network, and this means that it is not taken with the camera, so it will not present the same pattern that characterize real images. And in fact, also these generated images also present artificial fingerprints that we can extract from these images, and that are completely different from the fingerprints that we can extract from a real image. And in particular, if we observe the fingerprint in the frequency domain, so if we analyze the fingerprint of the image in not in the spatial domain but in the frequency domain using a Fourier analysis, you can see on the left a real image with the corresponding Fourier-based fingerprint, and on the right an AI-generated image where instead we have a quite very different fingerprint. In particular, you can see these peaks inside the image that characterize the AI-generated image, and these peaks are related to specific type of processing that are included in the synthetic generator. So they are clearly they are really clear clues that this image was artificially generated. And also, if we consider different type of generators, so on the top you have all different synthetic generators like Stable Diffusion, Big Gun, Style Guarantee, Glide, Taming Transformer. These are different type of synthetic generators that have been proposed in the recent years. And you can see that each of these synthetic generators produces a different artificial fingerprint with a different type of patterns. And this also means that we can sort of try to understand, to attribute the image to a specific type of generator. At the same time, there are also different type of generators that share the same fingerprint, which means that probably they have an architecture of, the architecture of the generator is very similar, so they can be they were like variations of a specific generator. For example, latent diffusion that was proposed a few years ago has some specific fingerprints that are also present in Midjourney V5, which is a tool that you can use over the web. Of course, you pay for that, but probably since the fingerprint is very similar, probably the architecture is similar to the one of latent diffusion. So it's true that all these synthetic generators can be different as soon as they were developed in different way, but they can also present some correlations one to another. Okay, so let's talk about the techniques that are developed and that are also based on artificial intelligence themselves, and that have been developed to detect to distinguish synthetic images from real ones. So first of all, why we are using AI? I mean, this is of course an arms race, and we use the most powerful detectors for synthetic images, videos, audios. They are all based on artificial intelligence. So actually, we use AI also for defending, not also for attacking maybe someone. And how good are these artificial intelligence-based forensic detectors? Now, note that all the detectors that are based on artificial intelligence require large data sets of real or fake data for training. So they actually learn from examples. The larger is the data set, the better they can actually distinguish. And the more diverse is the data set, the better, of course, are the performance. And I will show, okay, these are some examples in these tables of data sets that have been proposed in the recent years for, in particular, these ones were proposed for images. And as you can see from the numbers, I mean, the number of real and fake images that are present in these data sets are quite large. Now, what happens? Suppose that we train a detector on progressive growing gun, which is a specific synthetic generator. So we are actually training on progressive growing gun. And then we test not only on images from this specific synthetic generator, but also from different type of models like Big Gun, Style Gun 2, Style Gun 3, EG3D, Gigagun. And we evaluate the area under the curve, so the AUC. You can see that the performance, of course, are perfect on progressive growing gun. So you have exactly the same synthetic generator in training and in test. They are quite good for other type of gun-based generators, not so good for Gigagun, but okay, let's say that on average performance are quite good. But if we test this type of this detector on like diffusion models, so the more recent generators that are based on text, or on commercial tools like DALL-E 2, DALL-E 3, Midjourney, Firefly, you can see a very strong drop in terms of performance, which highlights the importance of the training data, which training data you are using for the detector. And if we change the data set used for training, we could say, okay, let's train on a diffusion models. Then, of course, the results will be very good on diffusion models and will be worse on generative adversarial models, maybe not so bad on the commercial tools because they are all based on diffusion models. And of course, one could say, okay, let's collect all the possible type of synthetic generators and put in training, but of course, this doesn't solve the problem because you can have new synthetic generators that are proposed, and you will never, also in this case, it's difficult to stay behind the technology and you should update continuously the detector. And so one main issue in this area is how to gain generalization. So how can we develop a strategy that is not influenced so much by the training data? One possible solution that you can find over the web that was proposed in 2020 is to apply augmentation. So this is a very simple solution, but it's really very much effective. So what you can do is consider like a very large data set. In this case, the proposal was to consider this progressive growing gun, and with very different type of categories, so different content, increase diversity of the data set, but at the same time also consider what is called augmentation. So not only the original data set, but also include compressed versions of the images or blurred versions of the images. In general, you can add some perturbed version of the images, and this increases both robustness and generalization. And here you can see some results. So here, again, you have the AUC, and on progressive growing GAN, it's perfect, it's 100%. And then I will show to you the result. Also, on other generators, they are still quite good. On JPEG compressed version of the images, which are like images that are have lower quality. So you can see that the performance are also quite good. But if you instead show accuracy, and accuracy is a very important measure because the AUC that I've shown to here in this slide doesn't take into account, is a measure that is not dependent by the threshold. So doesn't take into account at a certain point you have to make a decision and you need a threshold. And if you set the threshold in the middle at 0.5, then what happens is actually that the performance are not good. So there is also a problem of sensitivity to the threshold. So there is a problem of calibration. So it's important not only to have a good general detector, but also to have it that is well calibrated, so that can work well with a fixed threshold and irrespective of the type of generator. And other findings that have been done in the literature is in general to increase the diversity of the data set, to try to reduce the information of the images to avoid to reduce the information in the process. So, for example, never resize an image or reduce its dimension, but maybe consider crop patches on the images, because in this way we do not reduce the information that is embedded in the image. So we are not reducing those hidden traces that I've shown to you previously, because all these forensic invisible traces are really very weak, and some post-processing operations can reduce them significantly. And in this case, if we try to keep the information as best as possible, and also we do a proper augmentation, we can improve the performance. We are not solving the problem completely. These are always GAN-related images, but still, the performance can improve. In general, there are several possible strategies that one can apply towards generalization. I will show to you what we have done in our research, and in particular, we will focus on one-class learning and identity-based methods and zero-shot learning. So our approach to gain generalization is actually to avoid relying on fake data during training. And this means actually that we do not consider fake data in our procedure. So fake data are actually not used during training, not used at all. And this means that we can, in this way, we can reduce the dependence on the fake data and increase the generalization. And I will show to you 3 different strategies that we have developed in our research. And this is important because avoiding fake data during training can also reduce possible dataset bias. For example, there are many methods that use images that are often JPEG compressed, while synthetic images are in the PNG format, so are uncompressed. And this means that the dataset is actually biased. So when you evaluate the performance on test data that also present the same bias, the accuracy is very high. But then if you consider a compressed version of the images and you compress the fake images at, for example, quality 95, you can see that the performance drop. And also if we reduce the quality, they are even worse. So it's quite important to also try to avoid biases in training dataset. This is a very important point. And this also means that every time you use a detector, you should really know very well the way it was trained. Okay, so our approach to gain generalization is to model what is real and avoid to include fake data during training. And what we have done, so we have considered something that is similar to the PRNU, to the fingerprint, but is an alternative approach that is based on AI. So we try not to have any prior information on the device, no need of images coming from the very same device, which is required for PRNU. And we would like to exploit all possible in-camera artifacts, not only the artifacts that are related to the manufacturing process, so also the mosaicing, possible JPEG artifacts. And so what we have done, we have learned a camera fingerprint by collecting a very large number of real images. So we have collected around 1,500 different camera models. And then from this, from the images of these different camera models, we have extracted patches, so small blocks from these images, and tried to apply a procedure where we want to extract a fingerprint by considering that every image should have a different fingerprint if it comes from a different model, from a different position, and from a different possible editing strategy, while only patches from the images that are coming from the same camera model should be identical. In this way, we have extracted what we have called a noise print. And this is, here you can see this fingerprint. It's a fingerprint that highlights all the in-camera processing operations, and different camera models should have different fingerprints. And so here you have two different camera models, and you can see that the fingerprint is different. And here you see that this camera pattern is disrupted by possible manipulation, so by possible inconsistencies highlighted by the noise print. So the noise print can show possible inconsistencies. It's the same idea of PRNU, but this doesn't require any type of images from the camera, so any prior knowledge, and it's based on artificial intelligence, which means that, for example, if cameras will change over the years, it can be retrained and it can be easily updated. And another important thing that we have done is also to consider a confidence estimation. So sometimes it happens that on real images, false alarms can arise. And so you can maybe wrongly say that a real image was manipulated. And we have a confidence map that tells us which are the part of the images we can trust and which one we cannot trust, which helped a lot to reduce false alarms at image level. And note that right now there are also not only semantic manipulations that you can do, like adding or removing objects, but using the recent AI tools, you can also like expand an image using generated content. And you can notice that the noise print is actually understands that there are two different patterns from the real image and the generated one. This also highlights again that the fingerprint that is embedded in the image is different. And this is an extension to videos where you can see the face of Arnold Schwarzenegger was manipulated, and on the face of this actor there is this pattern which is not present instead on the face of the child. Another type of approach that we have proposed is to consider an identity-based approach. So instead of answering to the question, is this video manipulated? So we are looking for forensic inconsistencies. We are trying to answer to the question, is this person who is claimed to be? So trying to verify the biometric traits of an identity of a person. And this means that we are trying to understand if the biometrics are preserved. We do not train on videos of the person of interest, which is important, so that otherwise, I mean, this could be quite intensive in terms of number of hours. We also we train on a data set of different identities, 5,000 identities, and then the network is actually free, so we do not train it again. But during test, what we need is a collection of real videos of the claim identity, and then we actually answer to the question if the video is coherent with the reference set or not. This is quite helpful for like famous people, where we can or even for ourselves. I mean, we always have a set of pristine videos that we can make available and verify our identity. And we proposed actually this method that is based on facial features, but also extract temporal features. So it's based both on the face, but also on the way the face is moving, and can understand if an image a video was manipulated or not. Here there is an example that we have done on Nicolas Cage, who seems to be very, I mean, people like to manipulate his videos. So the first are real videos of Nicolas Cage, and the distance you can see is below a certain threshold. Now, setting this threshold is not obvious, and you need, of course, a validation set to indicate, to properly set it. Then the next videos are some deepfakes, and you can see that the distance increases. And here instead, it's not a deepfake, but it's an imitator. And this is interesting because this means that this type of identity-based methods can also distinguish an imitator. And the last one is a deep fake on the imitator. In this case, you can see that the distance is lower, still greater than the threshold, but in any case, the problem is becoming much more challenging. And we extended this method also to work in a setting where we considered also audio. And I can tell you that really the use of audio together with video was really very much important in the analysis, because right now it's really easy also to modify the voice of a person much more than the face. So there are using the voice is really very much important to obtain a good performance, and using together also. And we also try to exploit the power of pre-trained language models, so using like large pre-trained audio models to be included in our approach. And this was also very helpful for the analysis. So using pre-trained model on very large data sets also helped us to improve the performance. These are some results on realistic cases where we collected 10, 15 videos of the identity during test, and you can see again the distance of audio only and audio video compared to a threshold. Again, the setting of the threshold is not easy to do. So there are, of course, some challenges to face also in this case. And the last method that I want to tell you, which is always related to try to model the real data, takes inspiration from natural language processing, and in particular if we consider that, for example, some techniques that are used for synthetic text detection works in this way. So they are able to understand that text was generated by GPT, for example, because it follows a probabilistic model. So real text can be detected instead because it does not follow this model. So suppose, for example, you have this sentence, I saw a cat on a, which is the word which is likely to follow. Of course, there are a sort of distribution of the words that will follow this sentence with this prefix. And if you consider plain is very much surprising for GPT given the prefix. So this means that a human wrote the sentence. Instead, math is not surprising because it's following the same probabilistic model embedded in this in GPT, and so GPT wrote the sentence. This is the way some of the zero-shot method that are proposed in the literature work. And so what we did, we follow the same approach, but we switched the roles of real and fakes, and we proposed a probabilistic model of real images and detected the fake images as the images that were not following such model. And so synthetic images are like surprising for the real image model, and their actual coding cost differs significantly from what is expected. Okay, I will not go into the details of the method, just want to say that our approach is actually trying to understand if the fake image, so in this case, the image on the bottom, is following a certain model. If it is not following that model, then certain statistical features will differ significantly. And using some experiments that we have conducted, we were able to obtain a very high average AUC equal to around 90% without having any type of training of fake data during training. And what was interesting was that the threshold, the method was also sort of calibrated. So the threshold was almost the same for the different synthetic generators. Okay, so for sure, modeling the real images can help to generalize to unseen synthetic generators. We think this is a very interesting direction to follow. Low-level features can be powerful, but it's important to note that their strength can be reduced on like very low resolution or low quality data. So if you have like an image that was resized to, let's say, I don't know, 100 times 100 pixels, so it's 50 times 50, I mean, it's, of course, these hidden artifacts can be can be weak and can be even deleted. Also on low quality data, so if you compress an image a lot, the performance can of course get worse. Remember, these are hidden artifacts, and based on the quality of the data, they can be easily removed. For the identity-based method, the choice of the reference set can be quite challenging, but using a multimodal approach like video plus audio can significantly improve the performance. Overall, like in my experience of working in multimedia forensics since a long time, even if at the beginning there was not this AI generators, there was like using Photoshop and manipulating images and videos, you know, it took much more time, but in any case, there were like manipulations on data. So in a controlled scenario, AI-based detectors are very effective. So I would say that if you want to use a detector, first of all, you should know very well how it was trained on. And also, like the fingerprints can help to predict the performance of a detector. So if I know that my detector is very good in detecting synthetic images that present specific fingerprints, and these fingerprints are also present in the data that I included during test, then of course, I mean, this can help to reduce also the uncertainty about how the predictions of the detector, how the detector could work. And for example, this is what I told you at the beginning. So what we did as our first work on diffusion models was to train a model on latent diffusion. And then these mid-journey images came over the web, and our detector was very good. And we were happy, of course, but also surprised that it was so good on Midjourney. And then we understood that it was so good because the fingerprints were actually so similar that our detector was perfect for this type of test images. This doesn't mean that it's perfect for every type of synthetic detectors, even if we applied a very strong augmentation, as I told you before, that make it quite robust to different quality, different type of generators. But again, it's not difficult, it's not easy to predict. Again, okay, augmentation, I already told you, is very important. What is also important, and I experienced in my life, was in my research life, was fusion of complementary detectors. So, for example, we started to work in forensics in 2010, and in 2013 we joined a challenge, the IEEE Image Forensics Challenge, and you can see, for example, here the test image. And then we had two different detectors, a PRNU-based detector and a copy move detector. The copy move detector was able to detect if two objects were like, the same object, a copy, so same object that was like sort of rotated or slightly modified. And you can see that the fusion of the two methods could actually tell us the final results, which was, okay, the area manipulated was was the screen on the left. And also, this is another example. This is an image. This is the reference mask and the forged image. So in this case, two areas were manipulated. And if you run different detectors, maybe the copy move was able to detect this first manipulation. The noise print based was able to detect this other. Also, the color filter array based, this is another detector, was able to say there is something weird in some areas. This residual based was not able to say anything, and you can make sort of reasoning using the result of different detectors. So in general, it's important to rely on different detectors because they can detect different traces or complementary traces. Like another thing we noted that if we use a convolutional neural network-based detector and we consider a detector clip, which is instead based on pre-trained large vision models, the scores of these two detectors, as you can see in this plot, are sort of orthogonal. I mean, they do not completely overlap, which means that these two detectors can extract different information, and if we fuse them, we can improve the performance. We can improve the performance, for example, by varying JPEG quality, WebP compression. This is another format that is used a lot over the web, or against resizing. As I told you, if you reduce the scale of the image, the performance can decrease, but if you fuse the two detectors, you can have better results. What is not there yet? So what is still challenging is not solved. Okay, so what we do is actually try to distinguish what is fake, what is real. Now, I can tell you that the number of synthetic content over the web is increasing significantly. And probably most of this content is not actually malicious. Maybe it's made for fun, or maybe it's my avatar that was driven by me. And so I have my deep fake, and it's not really something that should be detected. So can we understand what is malicious, if there is a malicious intent in the manipulation or not? There is a recent work that has been done by NVIDIA, and they collected a dataset of deepfake videos where the deepfake was driven by the same person, so let's say an authorized deepfake and a different person. And this is interesting because, of course, we do not care about what is authorized, what is fine for the society, but only what is malicious. And this is something important, not analyzed and not fully developed yet. As I told you, dataset biases are very important and should be better considered. For example, I told you that we work on modeling the real image. Of course, we need a collection of real data. There are some datasets, and in particular, I can show here some examples of images from a dataset, this is probably a lion dataset, where can you tell if this is like a real image? I mean, some of these are like a cartoon, some of images are like computer graphics, or manipulated. So how can you tell this is pristine? And this is also something important to understand when working in this field. What is also very important is to develop fully explainable solutions. So often we try to understand why the forensic detector behaved in a specific way, but we cannot tell and we can always justify or motivate why it is working or not. Of course, it requires large data, and we cannot control perfectly the process. So this is also quite very, very important. Solutions should also be robust to possible adversarial attacks. So what is an adversarial attack? Again, I told you this is an arms race. So you can, for example, add adversarial noise to a video or to an image and make the detector fail and change the decision from fake to pristine. One should take into account that adversarial perturbations could be applied. Another thing one can do, and this is a very also interesting attack scenario, is to take a real image and insert in the real image, which are like actually the fingerprint of the artificial images, using a procedure that, okay, I'm not going to do detail, but what you can do is taking a real image and inserting easily the artificial fingerprint. And you can see here, this is from the left, it's the real image with the fingerprint in the frequency domain. And the second and third column are two synthetic images. What can be done very easily is to take the real images and introduce this synthetic fingerprint. And of course, I mean, you know, this is of course not easy to detect. For example, a clip-based detector is still able to distinguish the real, the synthetic images from the, let's say, the laundered ones, the ones that have been manipulated by the attacker, while this same behavior is not present in a CNN-based detector. So it depends also on the detector and how it was trained, which type of forensic clues this detector is looking at. But so again, it's important to consider different detectors, not just one. Oh, sorry. Was finished. Okay. And finally, beyond the solutions robust to possible adversarial attacks, detectors ready to use in the wild. Okay, right now, I believe it's not easy to have a detector that is can be used by everyone. Just I want to tell you about this work that was published recently in 2024, and they actually analyzed all the multiple copies that are present over the internet and noticed occurs that the performance gets worse on images that are processed multiple times. You can see from the initial sharing, and then there are, modified images, cropped images, resized, partially manipulated, reposted, and of course the first image it can be detected by a forensic detector much better than images that have been post-processed multiple times. So, for example, it would be really important to try to retrieve the first initial sharing of the image when testing a detector. In general, there is a lot of effort in the community. The most promising solutions, again, are based on artificial intelligence, but it's very important when using such solutions to understand which are the training data that were used for the detector in order to understand which are the capability, which are the limitations, and also the fact that especially on very realistic images, these detectors are exploiting invisible forensic clues. Then it's important to look for the best quality version of the test image over the web in order to understand what the detector, in order to improve the performance of the detector, because of course, these forensic artifacts are still there and have not been removed. Okay, so I was a bit longer, but I can stay a bit more so that you can make questions.
Thank you very much, Luisa. That was really impressive. I'm really impressed and reassured, let's say, with the incredible amount of research in the field of synthetic media. Really, I was very ignorant on the subject, and that's quite an incredible discovery for me. I don't know if there are any questions from the audience coming through. If not, I may have a couple. There is somebody from, we have Alan, and the question is, how consistent is the FP? I don't know what it stands for.
Fingerprint?
The fingerprint, yes, correct. For a given camera model, is it mainly a function of the sensor and components which could change as the supply chain changes?
Yes, it could change. In fact, so it really depends a lot on the hardware, but also all the in-camera processing. We noted that even different versions of same brands have different fingerprints, which means that sometimes they change the demosaicing algorithm or maybe some internal processing. Even the most recent cameras are very different. They even have not only one camera, but more cameras. It's not, in fact, PRNU right now on the old PRNU is more difficult to extract, and this is the reason for which it's important to consider like these AI-based models, because they can adapt to the newer devices, newer cameras that are developed, and so one can extract a more powerful fingerprint compared to what was done in the past, where there was everything was model based, and they were very hard to adapt to the technology. But you're right, yes, it could change as the supply chain changes. Good thing of the extractor we have developed is that you don't have to retrain it, or the camera model should not be inside the ones that were used for training. So it actually works even if the model was not present in training. But of course, suppose that all the devices are completely different from what we used in training, then of course one should retrain on newer devices. Right now we are using the ones that we developed like 7 years ago, 6 years ago, and it still works well. And of course, the ones that collected much more data works a bit better. Right. This is a watermark. So as I told you, we develop passive methods, so not active methods. So a watermark means that we are like we inserted the signature inside the image, a watermark, and then we can protect the image in this way. If you have the possibility to insert a watermark, for sure, I mean, this is the right way to go. The main problem, of course, is that I can remove the watermark. I can reduce the strength of the watermark. I mean, there are similar problems because the watermark is typically invisible, is hidden, and it's not easy to for the watermark to stay there without any type of also a post-processing, but also some attacks can reduce the strength of the watermark. In general, I believe that one should work in different areas, like do passive methods, the active methods, and then understand based on the scenario, based on the problem, which is the best to be used. But overall, I believe that, yes, I think that working on active methods is a very important direction. Right now, we are not ready because, I mean, our cameras do not embed or include the watermarking images. But yes.
Thank you very much, says Alan. Thank you, Alan. Okay, we're reaching really almost 4:03. And are there any other questions? Well, in any case, if not, by all means, pay attention to what has appeared in the chat, because we have a little survey for our participants today, and as we share them at the end of our webinars, and also we will keep adding all the webinar recordings to the playlist, which you can find on our YouTube channel. And also, as a reminder, that Leo has just posted about next week webinar that will take place at the same time on Thursday. And it's about still focus on AI and on responsible and ethical use of AI. And it will be in the form of a chat, let's say, of between our colleague Andy Brobuck and Floortje Jorna from SURF. So, as I said earlier on, more information about our Cybersecurity Month campaign on the link just shared by Leonardo in the chat. And it's been a really incredibly such an eye-opener for all of us. At least it was for me, and I'm very grateful to Luisa for accepting to take part. I don't see any other questions, so I think we can set you free, Luisa, to back to your great research, and we look forward maybe to talk to you in the future to know where this research is going, where to see what the next stage is. Very fascinating, really important, as Cornelia says. So all I can say, thank you so much, and hope to see you, all of you, also next week for our webinar.
Okay, thank you very much. Bye. Goodbye.
Arrivederci. Ciao, Luisa.
Ciao.